10,
let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition and liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every generation believes it lives at the edge of a breakthrough. Every era is convinced that the greatest barriers have already fallen, and that the remaining ones are only temporary inconveniences. Distance, danger, and limitation are always framed as problems waiting for better tools. And when it comes to space, this belief becomes almost religious. We speak of the stars as if they are already half-claimed, destinations reserved for a future that feels inevitable simply because we want it to be. But history is littered with futures that once felt inevitable. For most of human existence, the world itself seemed impossibly large. Oceans were thought to be endless voids, swallowing ships whole. Maps faded into myth at their edges. To sail beyond familiar coasts was not exploration, it was suicide. And yet, over time, ships improved. Navigation sharpened, fear receded, the oceans yielded. Humanity learned a dangerous lesson from this success, that all limits are temporary and all frontiers eventually surrender. That lesson has followed us ever since. When flight was first imagined, it was dismissed as fantasy. Humans were not birds. Gravity was absolute. But engines grew stronger, materials lighter, and the sky opened. When sound itself was broken, when jets crossed continents in hours, it reinforced the same belief, that nature resists at first, then submits, that every wall eventually cracks. This pattern has trained us to expect victory over every boundary. And so when we look at the stars, we assume the same story will repeat. We assume that interstellar travel is merely the next ocean, the next sky, vast, intimidating, but ultimately conquerable. We imagine starships the way earlier generations imagined caravels and steamships, crude now, magnificent later, slow now, inevitable soon. But this assumption rests on a quiet error. Space is not an extension of Earth, and the universe is not obligated to repeat history. The problem is not that we underestimate the difficulty of interstellar travel. The problem is that we misunderstand its nature entirely. We treat it as an engineering challenge, when in reality it is a confrontation with fundamental limits. We assume that enough intelligence, time, and funding will dissolve the problem, because that is how problems have behaved before. But not all barriers are technological. Some are structural. Some are built into reality itself. History does not move in a straight line of endless expansion. It advances in bursts, then slows, then narrows. Many technologies reach ceilings not because imagination fails, but because returns collapse. Nuclear power was once imagined as energy too cheap to meter. It worked, but never delivered the boundless abundance promised. Supersonic passenger travel crossed the Atlantic in hours, then vanished under the weight of economics, physics, and practicality. Even space exploration itself peaked not when curiosity died, but when the cost of progress began to outweigh its benefits. Progress does not disappear, it concentrates. Interstellar travel lives inside this pattern, not outside it. We like to say that humans are a spacefaring species, but this is a flattering myth. We are a planetary species that has briefly learned to touch the edge of its cradle. Every human who has ever lived, every culture, every civilization, evolved under one sky, one gravity well, one protective magnetic field. Even our most ambitious steps into space have remained tethered. Low Earth orbit, lunar flybys, robotic probes. We have not escaped Earth. We have only leaned away from it, carefully, briefly, and with constant lifelines attached. And yet, the language we use suggests otherwise. We speak of colonizing Mars, of becoming multiplanetary, of spreading life into the cosmos. These phrases carry an assumption that expansion is necessary, that stagnation is death, and that survival demands outward movement. This assumption feels intuitive because it mirrors the history of empires and civilizations on Earth. Those that expanded survived longer. Those that did not were absorbed, conquered, or forgotten. Expansion feels like life's default strategy. But the universe does not operate on human instincts. On Earth, expansion was possible because environments were broadly compatible. Air was breathable, gravity was tolerable, water existed, biology transferred. Even hostile regions could be adapted to with tools, shelter, and time. Space offers none of this. It is not merely hostile, it is indifferent in a way Earth never was. There is no gradient of habitability waiting beyond our borders. There is only a sharp drop from survivable to lethal. This is where the illusion of the next frontier begins to fracture. When we imagine future starships, we picture continuity, human life carried outward, intact, familiar, recognizable. We imagine cities under domes, children born beneath alien suns, civilizations echoing Earth across the galaxy. But these images are not projections of reality. They are projections of desire. They are stories we tell ourselves because the alternative is uncomfortable, that we may already be living at the edge of where we can exist at all. This discomfort is not new. Civilizations throughout history have struggled to accept limits. Empires assumed permanence until collapse forced recognition. Financial systems assumed stability until trust vanished overnight. Each time the mistake was the same, mistaking momentum for inevitability, mistaking recent success for permanent permission. Interstellar optimism follows this same psychological path. We look at the rapid progress of the last century, rockets, satellites, probes reaching the edges of the solar system, and extrapolate forward in a straight line. If we could go from horses to rockets in 100 years, surely another 100 will take us to the stars. But technological curves do not extend forever. They bend, they flatten, they end. And when they do, progress becomes incremental rather than transformative. The illusion lies in assuming that distance scales like difficulty, that traveling 100 times farther simply requires 100 times more effort. In reality, some thresholds are non-linear. Some distances are not harder, they are categorically different. Interstellar space is one of those thresholds. Between planets, space is vast but navigable. Between stars, it becomes something else entirely. Not an empty highway, but a void so sparse that even collision becomes dangerous. Not a vacuum that merely lacks air, but an environment saturated with radiation, time dilation, and isolation, measured not in months or years, but in generations. And yet, popular culture trains us to ignore this. Science fiction collapses distances into scenes. Ships jump, crews sleep. Time becomes a narrative convenience. This is not deception, it is storytelling. But when these stories bleed into expectation, they create a false sense of feasibility. We begin to believe that because something can be imagined, it can be built. That because equations allow a possibility, reality will eventually cooperate. History warns us otherwise. There have always been ideas that were mathematically elegant and physically unreachable. Perfect engines, infinite energy loops, machines that promised more output than input. Each generation produced designs that appeared sound until reality asserted itself. The universe does not reward cleverness alone. It enforces constraints without apology. The belief that interstellar travel is inevitable is not grounded in physics. It is grounded in faith, faith in progress, faith in ingenuity, faith that tomorrow must always be bigger than today. But faith is not evidence. And when it comes to the stars, evidence is scarce and unforgiving. This does not mean that space exploration is pointless. It means that expectation must be disciplined by reality. There is a difference between reaching outward with curiosity and betting survival on escape. There is a difference between exploration and dependence. What makes this illusion dangerous is not that it inspires ambition, but that it distracts from limits that demand respect. When societies believe salvation lies elsewhere, they neglect the systems that sustain them here. When the future is imagined as infinite expansion, present fragility is easier to ignore. This pattern appears again and again. Empires overextended themselves, chasing distant gains while internal foundations weakened. Financial systems promised endless growth until leverage collapsed them. Each time, the warning signs were visible, but dismissed as temporary obstacles on the road to a brighter future. Interstellar travel occupies a similar psychological space. It offers a vision of escape so compelling that it risks becoming a substitute for restraint, adaptation, and responsibility. The most unsettling possibility is not that interstellar travel is difficult. It is that it may be fundamentally misaligned with human survival, that our future, if it exists at all, does not lie in scattering across the galaxy, but in learning how to endure on the rare island that already supports us. The universe is vast, but vastness is not an invitation. It is a condition, a fact, one that does not care whether we approve. And this brings us to the central tension that will shape everything that follows. Is interstellar travel merely delayed by technology, or is it constrained by reality in ways we have not yet fully accepted? To answer that, we must strip away intuition, optimism, and narrative comfort. We must replace them with scale, physics, biology, and time. Because the stars do not respond to belief, they respond only to laws. And those laws are far older, colder, and less negotiable than any frontier humanity has ever faced. Distance is one of the oldest illusions the human mind struggles to grasp. We evolved in landscapes where distance meant walking for hours, maybe days. A mountain was far, a sea was far. Even crossing a continent once felt unimaginable. Our intuition for distance is built on bodies that move slowly and environments that scale gently. The universe does not share this design. When we talk about interstellar travel, we often begin with a comforting phrase, the nearest star. The words make it sound approachable, almost modest, as if proximity exists on a cosmic scale, the way it does on Earth. But this phrase hides a brutal truth. In space, near is a deception created by numbers too large for instinct to process. The nearest star system to Earth, Proxima Centauri, is about 4.4 light-years away. That number is repeated so often it has lost its meaning. A light-year sounds like time, not distance, and that alone should warn us something unusual is happening. A light-year is not a measure of duration. It is a measure of how far light travels in 1 year, moving at the maximum speed the universe allows. That single unit already contains a quiet threat. The fastest thing that exists still needs years to cross the gap. To make this comprehensible, we have to abandon intuition and rebuild it from the ground up. Light travels at roughly 300,000 kilometers per second. In 1 second, it could circle Earth more than 7 times. In 1 minute, it travels farther than most humans will ever journey in a lifetime. In 1 year, it covers nearly 10 trillion kilometers. Multiply that by more than 4, and you begin to approach the distance to the closest star. Now consider this. Every spacecraft humanity has ever launched moves at speeds that are microscopic by comparison. Voyager 1, the fastest object to ever leave Earth's influence, travels at about 17 kilometers per second. At that speed, reaching Proxima Centauri would take over 70,000 years. Not decades, not centuries, tens of thousands of years. That is longer than the entire history of human civilization, longer than agriculture, longer than writing, longer than nations, religions, and languages have existed. And Voyager is not slowing down because we want it to. It is moving as fast as our physics and engineering have ever allowed a human-made object to move. This is not a budget problem. It is not a motivation problem. It is a scale problem. The universe is not just big, it is violently big. Within our solar system, distances already strain comprehension. Light takes more than 8 minutes to reach Earth from the Sun. Communications with Mars lag by up to 20 minutes one way. Commands sent to distant probes must anticipate the future, because by the time a signal arrives, the moment has already passed. Even within this relatively tiny cosmic neighborhood, real-time interaction collapses. Interstellar distances break something deeper: relevance. When travel times stretch beyond human lifespans, destinations stop being destinations and become abstractions. A journey that cannot be experienced by its initiators is no longer travel in the traditional sense. It becomes an inheritance problem, a promise passed forward with no guarantee of fulfillment. This is where the illusion quietly persists. We imagine faster engines solving the issue, as if speed increases linearly, as if doubling engine power halves travel time. But space does not reward brute force. Every increase in speed demands exponentially more energy. Rockets are punished by a cruel equation. The faster you want to go, the more fuel you need, and the more fuel you carry, the heavier you become, requiring even more fuel. This compounding effect is not a design flaw. It is physics asserting dominance. Chemical rockets, the kind that took humans to the moon, are already near their theoretical limits. Nuclear propulsion promises improvement, but not miracles. Even optimistic designs struggle to reach a fraction of a percent of light speed. At those velocities, interstellar travel still demands thousands of years, and this assumes something else rarely acknowledged: that speed is maintained indefinitely. Space is not frictionless in the way popular imagination suggests. It contains dust, sparse but deadly at high velocity. At interstellar speeds, a grain of sand carries the energy of a bomb. Shielding against this requires mass. Mass slows ships. Slower ships extend exposure time. Exposure increases risk. The system punishes excess in every direction. Even if we imagine propulsion breakthroughs that push ships to 10% of light speed, a level far beyond anything we can currently achieve, the journey to the nearest star still takes over 40 years. That is one way. No delays. No deceleration problems. No failures. Just 40 years inside a machine that must function perfectly the entire time. 40 years is not just time, it is erosion. During those decades, the outside universe does not pause. The civilization that launched the mission will change. Governments fall. Languages drift. Priorities shift. By the time the travelers arrive, they may belong to a forgotten past. Their mission could be obsolete before it ends. This temporal separation introduces a psychological distance that mirrors the physical one. Interstellar travel does not just separate locations, it separates eras. A ship leaving Earth is not just traveling through space, it is traveling into a future it cannot influence and a past it cannot return to. This has never been a problem humanity has faced before. Even the longest voyages on Earth maintained cultural and temporal continuity. Explorers returned home to societies that still recognize them. Interstellar travel breaks this loop entirely. It demands irreversible commitment with no feedback. A single decision locks generations into outcomes they cannot revise. Distance at this scale becomes destiny, and the illusion deepens when we zoom out further. Proxima Centauri is not an exception. It is the closest neighbor in a galaxy where the average separation between stars is measured in light years. Beyond that, galaxies themselves drift apart, accelerated by cosmic expansion. Some regions of the universe are already unreachable, even at light speed. Not because we are too slow, but because space itself is stretching faster than signals can cross it. This is the ultimate insult to intuition. Distance is not static. The universe grows. It pulls destinations away faster than we can chase them. There are stars we will never see as they are now, only as they were millions of years ago. There are regions whose light will never reach Earth at all. No technology can fix this. No engine can outrun expansion. Interstellar travel exists within this expanding framework. It is not a race on a fixed track. It is a pursuit on a surface that is constantly receding. This reality forces an uncomfortable conclusion. The universe is structured to discourage contact. Stars are isolated. Solar systems are islands. The vastness between them is not empty convenience, but enforced separation. This may not be intentional. The universe has no intent, but the effect is the same. Distance becomes a filter. Only signals, not bodies, pass easily. Information travels freely. Matter does not. This pattern is telling. We can observe the universe in extraordinary detail. We can detect planets hundreds of light years away. We can measure atmospheres, temperatures, compositions. The universe allows us to see almost everything, but touch almost nothing. Observation is cheap. Transportation is punishing. That asymmetry may not be accidental. On Earth, civilizations expanded physically because communication was slow and transport was comparatively cheap. In space, the balance flips. Communication is fast. Transport is nearly impossible. The universe seems optimized for awareness without access, knowledge without occupation. This raises a quiet but profound question. What if the purpose of intelligence is not to spread, but to understand? If that is the case, then interstellar travel may not be humanity's next step, but its misstep. A projection of terrestrial instincts onto a cosmic environment that does not support them. The illusion of manageable distance persists because our minds compress scale when numbers grow too large. Millions, billions, trillions, they blur together. But the universe does not blur. It enforces every meter, every second, every joule of energy with ruthless precision. Between stars, distance is not an inconvenience. It is the primary feature. And this feature reshapes everything: engineering, biology, culture, meaning. It forces us to confront the possibility that we are not meant to cross these gulfs physically. Not because we are unworthy, but because reality is structured otherwise. As we move forward in this exploration, the next question becomes unavoidable. If distance alone already strains the limits of plausibility, what happens when we confront the one barrier that no amount of cleverness has ever defeated? Speed. Because distance can sometimes be endured, but speed is enforced, and the universe enforces it absolutely. Every road humanity has ever traveled shared one comforting assumption: that speed could always increase. A horse could be replaced by a carriage by a train by an airplane. Each improvement collapsed distance and reshaped civilization. Speed became synonymous with progress. Faster meant better. Faster meant closer. Faster meant possible. This history trained us to believe something quietly radical: that speed has no ultimate ceiling, that limits exist only to be surpassed. And for most of human history, that belief appeared correct. Until we encountered the universe's first non-negotiable rule. In the early 20th century, Albert Einstein revealed a truth so counterintuitive that even physicists struggled to accept it. The speed of light is not just fast, it is absolute. It does not change depending on who measures it. It does not bend to ambition, technology, or perspective. It is the same for everyone, everywhere, under all conditions. This was not merely a discovery about light. It was a discovery about reality itself. The speed of light is not a suggestion. It is a boundary woven into the structure of space and time. And once something has mass, even the tiniest amount, approaching this boundary becomes exponentially harder. Not gradually, not inconveniently, exponentially. As an object accelerates, its energy requirements grow faster than its speed. Push harder, and instead of going much faster, the object becomes harder to push. Time itself begins to distort. Mass effectively increases. Space contracts. The universe resists acceleration, not with friction, but with geometry. This resistance is not something engineers can outsmart. It is not a flaw in current technology. It is how the universe enforces its rules. To reach the speed of light with a massive object would require infinite energy. Not an enormous amount. Not an unimaginable amount. Infinite. A quantity that cannot exist in reality. Which means, by definition, it cannot be achieved. This is where intuition fails completely. We are accustomed to limits being temporary. Engines improve. Materials improve. Efficiencies improve. But no amount of improvement can cross an infinite threshold. You can approach it forever. You can get closer and closer, but you will never arrive. This turns interstellar travel from a problem of ambition into a problem of asymptotes. You can chase the speed of light endlessly and still fall short, and every fraction closer costs more than the entire journey before it. This alone does not make interstellar travel impossible, but it reshapes it into something fundamentally alien to human experience. At 10% of light speed, a journey to the nearest star still takes over 40 years. At 50%, it takes about 9 years. But the energy required to reach and sustain that speed is beyond anything humanity has ever controlled. At 90%, the energy demands explode so violently that even hypothetical future civilizations struggle to justify them. And speed is only half the story. Because as velocity increases, time itself begins to fracture. Time dilation is not science fiction. It is experimentally verified. Clocks on fast-moving satellites tick slower than those on Earth. Astronauts aboard the International Space Station age fractions of a second less than people on the ground. At interstellar speeds, this effect becomes profound. For travelers moving near light speed, time slows dramatically relative to Earth. A journey that takes decades for the outside universe may take only years for those aboard the ship. At first glance, this seems like a gift, a loophole that allows distant travel within a human lifetime. But this loophole comes with a devastating cost. Time dilation does not shorten the universe's wait for you. It lengthens your separation from it. A crew that experiences 5 years aboard a near light-speed ship may return to find centuries have passed on Earth. Everyone they knew is gone. Their culture is history. Their language may be archaic. Their mission may be meaningless. They would not be explorers returning home. They would be artifacts arriving late. This breaks something essential about travel. Return. Exploration, as humanity understands it, depends on continuity. Knowledge is brought back. Experience is shared. Time dilation severs this loop. It turns journeys into one-way crossings between eras. And this assumes a return is even possible. Acceleration is only half of motion. Deceleration matters just as much. To slow down from near light speeds requires the same brutal energy investment as speeding up. Miss your timing and you don't arrive. You overshoot, flying past your destination forever, unable to turn back. The universe offers no brakes. This makes precision not merely important, but existential. A miscalculation does not cause delay, it causes disappearance. The popular imagination often glosses over this by invoking technologies that manipulate space itself. Warp drives, space-time bubbles, shortcuts through reality. These ideas are compelling because they promise speed without velocity, movement without motion, travel without consequence, but they rest on assumptions that collapse under scrutiny. Warp concepts require negative energy densities, forms of matter that have never been observed and may not exist. Wormholes require space-time structures that are violently unstable, collapsing the moment anything tries to pass through. Even if these structures could exist, keeping them open would require energy densities comparable to stars. Not large amounts of power, cosmic amounts. This is the pattern we keep encountering. Every attempt to bypass the speed limit does not merely demand advanced technology. It demands rewriting the conditions of existence. The universe does not merely say, "This is hard." It says, "This is not how I work." History is filled with moments like this, though less dramatic. Perpetual motion machines were once taken seriously by brilliant minds. They obeyed elegant logic until thermodynamics revealed an unbreakable constraint. You could imagine infinite motion, but entropy refused to cooperate. No clever mechanism escaped it. The universe enforced a rule, and imagination had to retreat. The speed of light plays a similar role, but on a grander scale. It is not a wall you can climb. It is a horizon you can approach forever without crossing. And yet, the illusion persists because we confuse theoretical permission with practical possibility. Physics equations may allow certain configurations under extreme conditions, but equations do not promise accessibility. They describe what would happen if such conditions existed. They do not guarantee that the universe ever produces them. This distinction matters. Because when we talk about interstellar travel, we often frame the challenge as one of insufficient progress, as if we are merely early, as if the future naturally contains answers to questions we cannot yet solve. This belief is comforting, but history suggests it is unreliable. Some problems are not solved. They are accepted. Human flight was solved because the atmosphere allowed it. Supersonic flight was limited because the atmosphere punished it. Nuclear fusion remains elusive not because we are foolish, but because conditions required for stable fusion are extraordinarily rare outside stars. Progress does not override reality. It negotiates with it, and sometimes loses. The universe's speed limit is not negotiable, and this has consequences beyond propulsion. Communication itself begins to fail at interstellar scales. Even light-speed signals take years to arrive. Conversations stretch across decades. Decisions are made blind. Coordination collapses. A civilization spread across stars would not be a civilization at all. It would be a collection of causally disconnected islands. This fragmentation undermines one of the deepest assumptions behind interstellar expansion: unity. We imagine a shared human future among the stars, but physics enforces separation so extreme that shared identity becomes impossible. Culture drifts faster than messages, values diverge, time splits societies apart. At that point, humanity becomes a historical label, not a living collective. This is not speculation. We see it on Earth. Isolated populations diverge within centuries. Language fractures. Belief systems mutate. Multiply that isolation by light years, and the process accelerates beyond recognition. The speed limit does not merely slow ships, it fractures meaning. And this may be the most profound implication of all. The universe allows intelligence to emerge. It allows awareness, reflection, curiosity. But it seems to resist consolidation. It resists empires. It resists cohesion beyond certain scales. It enforces locality, here, now, bounded. This raises an uncomfortable possibility that intelligence is meant to be local, not universal. That the universe supports minds, but discourages their spread. If this is true, then interstellar travel is not the next chapter of human progress. It is a misreading of the story entirely, a projection of terrestrial success onto a cosmic environment that does not share Earth's generosity. The speed of light stands as a quiet sentinel, not dramatic, not cruel, simply absolute. It does not threaten, it does not warn, it merely exists, and in existing, it defines what is reachable and what is not. Distance challenges endurance, speed challenges existence, and the universe has already chosen which one it will allow us to confront. As we move forward, another question emerges, one just as unforgiving. Even if we accept the speed limit, even if we design ships that crawl patiently between stars, what happens to the fragile biological creatures inside them? Because physics is only the first barrier. Biology is the next. When the limits of speed become unavoidable, imagination looks for detours. If you cannot move faster through space, then perhaps you can move space itself. If distance refuses to shrink, then maybe reality can be folded, bent, or bypassed. This is where interstellar optimism pivots, away from engines and fuel and toward loopholes. Warp drives, wormholes, shortcuts through space-time. These ideas feel different from rockets and propulsion. They feel smarter, cleaner, less brute force. Instead of fighting the universe, they promise to rearrange it. And because they appear in equations written by serious physicists, they carry a dangerous aura of legitimacy. They are often described not as fantasy, but as theoretically possible. But history teaches us to be cautious with that phrase. Theoretically possible does not mean achievable, it does not mean stable, and it certainly does not mean compatible with reality as it exists. Many things are allowed by mathematics that the universe simply never provides the conditions for. Warp drives and wormholes belong to this category. The idea of a warp drive, most famously formalized in the 1990s, is deceptively elegant. Instead of moving a ship through space, the ship sits still, while space contracts in front of it and expands behind it. Locally, nothing exceeds the speed of light. Globally, the ship appears to travel faster than light relative to distant observers. On paper, this seems to obey Einstein's rules while sneaking around their spirit. But the price of this maneuver is extraordinary. To create such a space-time bubble, the equations demand something the universe has never shown us in usable form: negative energy density. Not just small amounts, vast quantities. Regions of space where energy is not merely low, but less than nothing. This is not ordinary matter. It is not antimatter. It is something stranger, a condition where space-time itself behaves in reverse. Tiny hints of negative energy appear in quantum experiments under extremely constrained conditions. But scaling these fleeting effects to starship-sized space-time distortions is like trying to build a skyscraper out of soap bubbles. The math allows it. Reality does not cooperate. And even if such exotic energy existed, controlling it introduces another layer of impossibility. Negative energy is inherently unstable. It wants to collapse, disperse, or annihilate itself. Holding it in a precise configuration long enough to transport a ship would require control mechanisms more complex than anything physics has ever demonstrated. This is the first quiet truth about warp drives. They solve the speed problem by creating a far worse stability problem. Wormholes, often imagined as cosmic tunnels between distant points, suffer from similar issues. In theory, general relativity allows space-time to curve so extremely that two distant regions touch. A shortcut forms, distance collapses, travel becomes trivial. But in practice, every wormhole solution we know is catastrophically unstable. The moment anything with mass or energy approaches, the structure collapses. Keeping it open requires, again, negative energy, applied with perfect precision, indefinitely, not temporarily, not approximately, indefinitely. This demand for perfection is not incidental, it is fundamental. These space-time structures exist on the knife edge of collapse. Any deviation, thermal fluctuation, radiation, quantum noise, destroys them instantly. The universe, it seems, does not like holes in its fabric. There is also a deeper problem rarely discussed outside specialist circles: causality. Faster-than-light shortcuts do not merely allow travel, they allow paradoxes. If information or matter can arrive before it was sent, cause and effect unravel, time loops emerge, contradictions appear. The universe's ability to maintain a consistent history begins to break down. Physics responds to this threat harshly. Many models suggest that the universe enforces a kind of self-protection. Whenever a configuration would allow causality violations, quantum effects explode, destroying the structure before paradoxes can form. In simple terms, the universe may actively prevent time travel and faster-than-light shortcuts, not by forbidding them in equations, but by making them violently unstable. This idea is known as chronology protection. It is not proven, but it is suggestive. The pattern is familiar. Throughout history, humans have repeatedly discovered mechanisms that appear to promise infinite gain until a deeper rule intervenes. Leverage magnifies wealth until it magnifies collapse. Energy extraction increases productivity until entropy demands payment. Each time, the universe allows progress up to a point, then extracts a cost that cannot be ignored. Warp drives and wormholes feel like attempts to evade payment. They promise travel without time, motion without inertia, distance without cost. And in doing so, they violate a principle that appears again and again across physics. Nothing meaningful comes for free. There is also an engineering reality often overlooked. Even if a warp bubble or wormhole could be created once, maintaining it would require continuous energy input and flawless control. Interstellar travel would no longer be about reaching a destination. It would be about preventing catastrophic failure every second along the way. One fluctuation and the ship is crushed, torn apart, or erased from causality entirely. This is not exploration, it is roulette at cosmic scale. Supporters of these ideas often respond by pointing out that many technologies once seemed impossible. Flight, electricity, nuclear energy. They argue that skepticism reflects a lack of imagination, but this comparison misunderstands the nature of impossibility. Those earlier breakthroughs operated within known physical frameworks. They were constrained, but not forbidden. Warp drives and wormholes are different. They demand conditions that may not exist anywhere in the universe except fleetingly and on microscopic scales. This is the difference between difficulty and absence. A mountain is difficult to climb. A vacuum is impossible to breathe. No amount of training overcomes the latter. History offers countless examples of ideas that survived on paper but died in reality. Alchemy promised transmutation until chemistry revealed atomic structure. Ether theories explained light until experiments proved the medium non-existent. Each time, elegant ideas collapsed under empirical weight. Warp drives and wormholes may follow the same trajectory, not as embarrassments, but as necessary dead ends. They show us what equations allow in abstraction and what reality refuses to instantiate. There is also a psychological dimension to their appeal. These concepts preserve a comforting narrative, that the universe's limits are negotiable, that cleverness always finds a back door, that destiny bends for intelligence. This belief is deeply human. It has fueled exploration, innovation, and survival. But it also blinds us to boundaries that require adaptation rather than defiance. The danger is not believing in warp drives. The danger is structuring expectations around them. When societies plan futures based on hypothetical breakthroughs rather than existing constraints, they risk neglecting the systems that actually sustain them. They postpone difficult decisions, trusting that tomorrow's miracle will solve today's limits. History shows how this ends. Civilizations that bet on endless expansion ignored soil depletion, water scarcity, social fragmentation. When growth stalled, collapse followed. The belief in future escape delayed present responsibility. Interstellar fantasies can play the same role. They offer an implicit promise that no matter how strained Earth becomes, the stars are waiting. That even if we fail here, somewhere else will redeem us. But if the shortcuts to those stars remain permanently closed, this promise becomes dangerous illusion. The universe does not advertise its boundaries with signs. It enforces them through consequence. Warp drives and wormholes may remain valuable as thought experiments. They stretch our understanding. They test the edges of theory. But treating them as pending technologies is a category error. It confuses imagination with feasibility and possibility with permission. The deeper lesson is not that these ideas are foolish. It is that the universe appears to tolerate intelligence only within certain domains. It allows understanding to spread far beyond reach. It permits knowledge without possession, observation without conquest. This asymmetry is striking. We can see galaxies billions of light years away. We can measure their composition, their motion, their history. The universe invites us to know it. But when we try to enter it, to cross its great distances physically, the resistance becomes overwhelming. Perhaps this is not a flaw. Perhaps it is the design, not a design by intention, but by outcome. A universe where awareness is cheap, but movement is expensive. Where wisdom scales faster than power. Where intelligence is encouraged to reflect, not to dominate. If that is true, then warp drives and wormholes are not missing technologies. They are misinterpretations of the relationship between mind and cosmos. The universe does not challenge us to escape it. It challenges us to understand our place within it, and that brings us to the next, unavoidable barrier. Even if we accept slow travel, even if we abandon shortcuts and loopholes, even if we resign ourselves to centuries-long journeys at sub-light speeds, what happens to the fragile biological beings inside those ships? Because physics may allow patience, but biology demands care. Even if distance could be endured, there remains a quieter enemy, one that cannot be shielded against, outrun, or engineered away: time. Physics often dominates discussions of interstellar travel. Speeds, energies, propulsion limits. But once those arguments fade, once we imagine ships that can coast between stars at a fraction of light speed, a deeper problem emerges. A problem not of motion, but of duration. Interstellar travel is not merely about crossing space. It is about surviving time. A journey to the nearest star system, even under optimistic assumptions, would take decades. More realistic scenarios stretch into centuries. And beyond that, travel to more distant regions of the galaxy would unfold across millennia. This scale of time is not just inconvenient. It is incompatible with how life on Earth functions. Human biology evolved for short arcs. We mature quickly, age rapidly, and deteriorate predictably. Our bodies are temporary structures, optimized for reproduction and adaptation within a narrow environmental window. Outside that window, failure accelerates. No technology has ever reversed this reality. At best, it delays it slightly. Cryogenic sleep is often proposed as a solution. Freeze the travelers, pause biology, resume life upon arrival. But this idea rests on a misunderstanding of how living systems work. Cells are not machines that can be powered down and restarted at will. They are dynamic processes. Metabolism, repair, signaling. These are continuous. Interrupt them and damage accumulates. Even with modern cryopreservation, we can only freeze very small biological samples, and even then, survival rates are limited. Scaling this to entire human bodies, preserving brains, organs, and identity without degradation, remains entirely speculative. And speculative does not mean imminent. But even if cryogenic technology were perfected, time would still extract its cost, not from the travelers, but from everything else. Civilizations are not static. Cultures shift, languages evolve, knowledge decays. The people who launch a starship will not be the people who receive it. A ship departing Earth today, bound for a star 50 light years away, would arrive in a future that no longer remembers why it was sent. This is not a hypothetical concern, it has precedent. On Earth, human institutions struggle to preserve continuity across centuries. Empires rise and collapse. Archives burn. Technologies are forgotten and rediscovered. Even stable civilizations rewrite their values within a few generations. Interstellar travel demands continuity on a scale no society has ever demonstrated. The mission must remain funded, relevant, and supported across political shifts, economic cycles, and cultural revolutions. The destination must still matter centuries later. The knowledge required to receive and integrate the travelers must survive intact. This is a staggering requirement, and if the mission is automated, crewless, the problem only shifts. Machines degrade. Software becomes obsolete. Maintenance requires intervention. Redundancy increases mass and complexity. The longer the mission, the higher the probability of failure. Time multiplies risk. Every year adds radiation exposure, micrometeoroid impacts, material fatigue, and system drift. Redundancy can delay failure, but never eliminate it. Eventually, entropy wins. Even the interstellar medium itself is hostile, sparse but relentless. High-energy particles penetrate shielding. Over decades, they damage electronics, mutate DNA, and weaken structural materials. Shielding thick enough to fully protect a crew would dramatically increase mass, slowing travel further and compounding the problem. And then there is psychology. Human minds are not designed for isolation over generations. Long-duration confinement already produces measurable cognitive and emotional strain in astronauts after months. Depression, anxiety, identity fragmentation, social conflict, these emerge quickly, even with constant communication with Earth. Remove Earth, remove real-time contact, stretch isolation into decades or lifetimes. Now the mission is no longer exploration. It is a social experiment with no reset button. Some propose generation ships, vast vessels where humans live, reproduce, and die en route. their descendants inheriting the mission. This idea acknowledges time, but underestimates it. Cultures inside closed systems drift rapidly, values mutate, myths replace facts. After a few generations, the original mission becomes legend. After many, it becomes irrelevant. The stars are no longer a destination. The ship itself becomes the world. At that point, arrival is not success. It is disruption. The descendants did not choose the mission. They did not consent to the destination. For them, arrival is exile, forced relocation to an alien world in the name of ancestors they never knew. This is not science fiction melodrama. It is sociological inevitability. Time changes meaning. Even if a crew somehow remains motivated, psychologically stable, and biologically intact, they face another challenge: relevance. Science advances rapidly. A ship launched with cutting-edge technology becomes obsolete before it exits the solar system. By the time it arrives, its systems may be primitive compared to those left behind, or those that followed later using better methods. Faster ships launched decades later may overtake it. The pioneers arrive last. This creates a paradox. The more time passes, the less sense it makes to leave. Waiting becomes rational. And so interstellar travel stalls, not because it is impossible, but because it is always premature. There is always a better engine tomorrow, a more efficient system, a safer design. The optimal launch date perpetually recedes into the future. Time, again, wins. There is also a deeper biological truth often ignored. Life is not just fragile, it is contextual. Human bodies are tuned to Earth's gravity, radiation levels, magnetic field, and circadian rhythms. Remove these, and subtle damage accumulates. Bone density decreases, muscles weaken, vision alters, immune systems dysregulate. These effects are measurable after months in microgravity. Over years or decades, they become debilitating. Artificial gravity can mitigate some issues, but introduces others. Mechanical stress, rotational sickness, structural complexity. Every solution creates new failure modes, and none address the core issue. Humans are Earth-adapted organisms attempting to become interstellar entities. Evolution did not prepare us for this. Time also erodes purpose. On Earth, goals are bounded by lifespans. They are achievable. Meaning is reinforced by completion. Interstellar missions dissolve this structure. When success lies beyond one's lifetime, motivation becomes abstract. Abstract motivation is weak. This is why human projects historically rely on near-term rewards and feedback. Even monumental structures like cathedrals were built with invisible progress across generations. The builders could see their work take shape. Interstellar travel offers no such reinforcement, only delay, and delay breeds doubt. Eventually, the question emerges: why endure this? Why sacrifice generations, resources, and stability for destinations that may be inhospitable, unreachable, or irrelevant by arrival? Time forces this question. It strips away romance and leaves accounting. Even if all technical barriers were solved, propulsion, shielding, life support, time remains undefeated. It transforms every solution into a temporary patch. It turns ambition into maintenance. It converts exploration into endurance. And endurance is not inspiring. It is exhausting. This is why, throughout history, humanity expanded across Earth, but hesitated at the oceans, deserts, and polar regions until technology compressed time. Steamships shortened voyages. Aircraft erased weeks of travel. Communication collapsed distance. Interstellar travel offers no such compression. Light itself sets the pace, and so time becomes the final filter. Not a wall, but a slope, gentle at first, then increasingly steep. Each additional year compounds complexity, risk, and meaning loss. Eventually, progress grinds to zero. The stars do not reject us violently. They simply wait us out. Perhaps this is the universe's most subtle constraint. not an explicit prohibition, but an indifference to our timelines. Galaxies evolve over billions of years. Stars live and die unconcerned with centuries. Against this backdrop, human urgency is noise. We want to go now. The universe does not care when. And in that mismatch, interstellar dreams quietly fade, not with explosions or failure, but with postponement, with committees, with feasibility studies, with plans always deferred to the next generation. Time does not need to stop us. It only needs to outlast us. And that leads to the most unsettling possibility of all. What if interstellar travel is not impossible, but irrelevant? What if intelligence is meant to understand the universe, not traverse it? To map it mentally, not physically? To adapt inward, not outward? If so, then the true frontier is not between stars, but within limits. And that brings us to the final question this journey must face. If we cannot escape our cosmic neighborhood, what does that mean for the future of intelligence itself? The universe does not merely challenge speed, distance, or biology. It challenges comprehension itself. Interstellar travel is a struggle not only against space and time, but against the very limits of intelligence. Every plan, every calculation, every design, every dream of crossing light years eventually encounters a quiet, immutable ceiling. The cosmos itself does not scale to minds the way Earth does. We tend to think of intelligence as an asset without boundaries, as if once a mind emerges, it can expand indefinitely, adapt perfectly, and conquer every environment it encounters. We imagine civilizations growing exponentially, conquering planets, constructing Dyson spheres, spreading through galaxies. These visions are seductive because they follow the logic of growth familiar to us. Expansion is always the reward for ingenuity on Earth. The faster, smarter, or more organized you are, the more territory you can claim. But the universe is not Earth. Its structure is hostile to the very process of exponential scaling. And this hostility is subtle. It does not announce itself with crashing asteroids or radiation bursts. It is enforced silently, patiently, across distances and epochs. To begin, consider observation itself. Intelligence relies on information. The more complex the environment, the more data required to understand it. In interstellar space, the flow of information is throttled by the speed of light. A signal takes years to reach even the nearest stars. Planets orbiting distant suns are not objects one can observe in real time. Light carries history, not presence. When you measure a star, you see it as it was years ago, sometimes millions of years ago, not as it is now. This lag creates a fundamental barrier. Intelligence cannot react instantaneously to distant events. Planning and adaptation, the core processes of intelligent life, are delayed by cosmic scale. Decision-making becomes slow, uncertain, and risky. A strategy that works locally fails catastrophically across light years. The further you try to extend your influence, the more fragile your control becomes. Then there is energy. Intelligence cannot exist without it. Computation, processing, life itself, all demand usable energy. On Earth, energy is abundant relative to human needs. The sun provides enough to sustain all life many times over. The planet stores energy in countless forms: chemical, thermal, gravitational, nuclear. Civilization learned to harness it efficiently. Expansion beyond the solar system, however, confronts a stark reality. Energy diminishes with distance. Stars are isolated. Even the nearest sun offers only infinitesimal energy to a traveler many light years away. The practical limits of computation, of life, of civilization, are bounded by what energy can sustain at any given location. This is not just an engineering problem, it is fundamental. Energy sets the maximum rate at which information can be processed, the maximum scale at which life can operate, and the maximum reach of any project. No matter how clever, no matter how resourceful, intelligence cannot outthink energy. It can optimize, it can conserve, it can allocate, but it cannot conjure what does not exist. Entropy adds a second, relentless boundary. Every process, every computation, every movement produces disorder. On Earth, this is mitigated by local reservoirs, the planet's heat sinks, chemical stores, and magnetic fields. In deep space, there are no such buffers. Heat dissipates into near-perfect vacuum. Materials degrade. Radiation gradually damages every system. Time compounds these effects. Even a perfectly designed starship slowly deteriorates under the universal rules. Intelligence can postpone entropy, but cannot eliminate it. This creates a subtle but profound constraint. Unlike distance or speed, which can be measured and overcome with effort or technology, entropy enforces a temporal ceiling. A civilization's capacity to maintain complexity decays as the universe's natural processes erode its substrates. Minds, machines, and social structures all suffer. In space, isolation magnifies this erosion. Decades of drift, centuries of separation, and millennia of delay all conspire to reduce the efficacy of intelligent systems. Now, consider complexity. Intelligence is not simply the ability to process information. It is the ability to act meaningfully on it. Decision-making, planning, engineering, social coordination. These are all functions of complex networks, whether neural or artificial. But complexity scales poorly in isolation. Within a small habitat, communication is rapid, feedback is immediate, and adaptation occurs in real time. Spread the same intelligence across light years, and the feedback loops collapse. Actions produce consequences years later, too late to adjust strategies. Knowledge becomes stale, coordination becomes impossible. Civilization fragments into disconnected nodes, each effectively isolated. Intelligence exists, but its capacity to influence diminishes with scale. This may explain why interstellar civilizations, if they exist, are either silent or exceptionally rare. A species capable of surviving across light years would face exponential delays in information, resource management, and social cohesion. The universe enforces distance not only physically, but cognitively. It ensures that intelligence must operate locally, not globally. That understanding, observation, and adaptation are achievable, but domination across the cosmos is effectively impossible. This boundary is mirrored in another subtle limit: perception. All senses, whether biological or artificial, are local. You can measure electromagnetic radiation, gravitational waves, particle flux, but only where you are. To extend perception requires probes, signals, or intermediaries, each bound by energy, time, and the speed of light. Intelligence cannot directly perceive distant stars or planets. It can only reconstruct models based on delayed, incomplete, and imperfect information. Uncertainty accumulates with distance, creating blind spots that can never be fully corrected. The universe ensures that knowledge becomes probabilistic and contingent at large scales. Even with artificial intelligence, this boundary persists. Computers can calculate faster than humans, but they remain bound by physics. Processing requires energy. Memory requires storage. Communication requires transmission. No algorithm can transcend these limits. A superintelligent system may outthink any human, but it cannot outscale physics. The cosmic constraints on distance, energy, and time apply universally. There is also the psychological component. Intelligence is not merely computation, it is consciousness, reflection, and subjective experience. For long-duration interstellar travel or dispersed civilizations, isolation imposes cognitive challenges. Generational drift, cultural divergence, and loss of shared context degrade collective intelligence. Even perfect machines must be programmed and maintained by humans or human-like cognition, which is fragile. Intelligence may survive, but it does so increasingly disconnected from its origin, its purpose, and its context. And yet, there is one paradoxical advantage. Intelligence, unlike life or matter, can encode itself. Knowledge can be transmitted across distances as signals stored in durable media, replicated redundantly. Civilizations can reach beyond physical constraints through information alone. Observation scales faster than presence. Understanding can expand even where travel cannot. This may explain why the universe appears so empty. Physical expansion is punished by time, energy, and entropy, but information can flow freely. Intelligence may leave imprints across galaxies without leaving matter behind. This asymmetry is profound. It suggests that the universe favors minds that observe rather than occupy, that model rather than manipulate, that calculate rather than conquer. The cosmic limit of intelligence is not a ban on thinking. It is a limit on doing. Knowledge can transcend distance. Action cannot. Presence is costly. Observation is cheap. And in this tension lies the subtle rule of the cosmos. Ultimately, the cosmic limit is a combination of barriers we have already seen. Distance enforces isolation. Speed enforces energy ceilings. Time enforces decay. Entropy enforces degradation. Perception enforces locality. Together, they create a natural horizon beyond which even the most capable intelligence cannot effectively operate in the physical domain. Civilizations may persist, but they do so within bubbles of causally connected space. Stars beyond these bubbles are unreachable, not due to lack of technology, but because physics itself ensures that attempts to reach them are self-defeating or prohibitively costly. The universe does not forbid intelligence. It contains it, corrals it, and defines its effective domain. And this leads to a humbling realization. Our drive to spread across the stars may be fundamentally misaligned with the cosmos. We can imagine travel, conquest, or expansion, because our minds evolved in a world where distance is surmountable and resources are accessible. But the universe scales differently. What is trivial on Earth becomes insurmountable at interstellar scales. Our intuitions fail. Our dreams clash with reality. Yet, there is a lesson hidden within this constraint. The limits do not demand despair. They demand adaptation. Intelligence may thrive not by moving stars, but by understanding them, by observing, modeling, predicting, and interacting within causal horizons, by creating knowledge networks that transmit across light years without physically moving matter, by embracing patience and locality rather than force and expansion. In other words, survival and flourishing may depend not on escape, but on mastery. Mastery of the environment, mastery of physics, mastery of information, and mastery of time. Interstellar travel, if it ever occurs, will be secondary. Understanding will come first. Observation, modeling, and cautious interaction will define the frontier of intelligence. Physical expansion may be aspirational. Conceptual expansion is inevitable. This perspective reframes the question of interstellar travel. It is not simply about propulsion, speed, or engineering. It is about aligning ambition with cosmic reality. It is about recognizing the ceilings imposed by time, distance, energy, and entropy, and asking, what can intelligence achieve within these limits? How can consciousness flourish without violating physics? How can knowledge accumulate across centuries, millennia, or even eons? The universe is vast, indifferent, and exacting. It rewards understanding more than action. It favors minds that calculate, observe, and adapt over those that attempt to conquer space. And it imposes a horizon beyond which physical presence is effectively impossible. This horizon may define the ultimate frontier, not stars themselves, but the edges of causally connected reality. Beyond them lies isolation. Beyond them lies impossibility. Beyond them lies a reminder that even intelligence is subject to cosmic limits. Even after confronting the immovable speed limit, the relentless passage of time, and the cosmic constraints on intelligence, one might imagine a final escape: engineering. Perhaps with enough ingenuity, we can build vessels strong enough to withstand radiation, durable enough to last centuries, and sophisticated enough to protect their passengers across the interstellar void. This is the hope that has fueled science fiction for generations. Enormous ships, perfect systems, and technology so advanced that physics itself seems secondary. But the universe is patient, and it waits for engineering optimism to collide with reality. Every aspect of a spacecraft must contend with reality in unforgiving detail. Unlike Earth, where the environment can be controlled, interstellar space is a domain where even the tiniest imperfection is amplified over time. Materials that seem strong in laboratories may fail under the sustained pressures of decades in vacuum. Metals can fatigue in ways that are impossible to anticipate without centuries of observation. Ceramics can crack under minute thermal stresses. Even composites, the crown jewels of modern engineering, degrade under relentless cosmic radiation. Every molecule becomes a potential point of failure. Every junction, seam, and weld a potential catastrophe. Consider radiation. In interstellar space, cosmic rays and high-energy particles bombard every object continuously. Shielding can reduce exposure, but it comes at a cost. Dense shielding increases mass. Mass increases propulsion requirements. More propulsion demands more energy. Energy requires fuel, power systems, or reactors, each adding mass and complexity. Even the best designs cannot completely eliminate radiation exposure. Microelectronics accumulate errors, sensors drift, structural materials weaken, biological tissues suffer mutations. Over decades or centuries, these effects are cumulative and inexorably destructive. Temperature extremes add another layer of complexity. In the cold of interstellar space, heat radiates away from the ship relentlessly. Maintaining a habitable environment requires insulation, active heating, and energy. Solar power becomes irrelevant far from stars, forcing reactors or stored energy systems. Conversely, parts of the ship exposed to starlight may heat uncontrollably. Thermal cycles induce expansion and contraction, stressing materials at microscopic scales. Tiny variations, repeated millions of times, can propagate cracks, break welds, and compromise structural integrity. For a vessel designed to last generations, these are not minor concerns, they are existential threats. Propulsion itself is an engineering nightmare. The energy required to reach even a fraction of light speed is enormous. Chemical rockets are hopeless. Nuclear thermal propulsion is orders of magnitude better, but still insufficient for interstellar distances within human lifetimes. Hypothetical propulsion methods, antimatter engines, fusion drives, laser sails, all demand precise engineering on scales humanity has never achieved. Containment of antimatter, stable and controlled fusion reactions, alignment of laser arrays across astronomical distances. Each is a frontier problem. Failure at any point is catastrophic. A minor misalignment, a small containment breach, a single miscalculated burn. Any could destroy decades of effort in an instant. And then there is redundancy. Any serious interstellar ship must be designed with multiple layers of backup, duplicate life support, power systems, propulsion, and navigation. But redundancy adds mass, which in turn requires more propulsion, more energy, and more shielding. Systems become increasingly interdependent, creating a complex web where failure in one area can cascade unpredictably. Engineering is not merely additive, it is multiplicative. Every additional safety system increases the probability that a rare, unexpected failure will occur. The paradox of redundancy is that, beyond a certain point, adding more fails to make a system safer. It simply introduces new failure modes. Navigation is another unforgiving domain. Over vast distances, tiny errors in trajectory can accumulate into massive deviations. A millimeter per second misalignment at launch can result in missing a target star by light years decades later. Mid-course corrections require sensors that can operate reliably over decades, thrusters that can function after prolonged storage, and calculations that remain accurate despite drift in systems and uncertainty in measurements. interstellar navigation is not a task of skill. It is a battle against cumulative error, and nature rarely forgives miscalculations over cosmic scales. Life support introduces yet another cascade of engineering challenges. Recycling air, water, and food is theoretically possible, but only if systems are perfect. Microbial contamination, chemical imbalances, and mechanical degradation accumulate slowly but relentlessly. Small leaks or malfunctions may go unnoticed for months or years, becoming crises before they are discovered. The longer the mission, the more unpredictable interactions emerge. Systems that function flawlessly for a few years may fail catastrophically over decades or centuries. Unlike laboratory simulations, the universe does not pause. Errors compound invisibly. Even the human body itself becomes an engineering challenge. Microgravity, cosmic radiation, isolation, and limited resources conspire to degrade physical and mental health. Muscle atrophy, bone loss, cognitive decline, and psychosocial stress are inevitable without extraordinary intervention. Countermeasures, artificial gravity, exercise regimens, medical interventions require systems that themselves are prone to failure. The crew is both payload and liability. Protecting them over interstellar timescales is as much a materials problem as a biological one. Maintenance is the silent killer of long-duration missions. No matter how reliable a system seems, every moving part wears. Lubricants degrade, metals fatigue, electronics drift. Robots can repair many failures, but they themselves are subject to the same constraints as the rest of the ship. Human maintenance is constrained by limited resources, time, and exposure. Every repair introduces risk. Every improvisation can become a new failure point. The longer the journey, the more unanticipated problems accumulate. Communication compounds engineering difficulty. Signals across light years arrive with years of delay. Real-time troubleshooting is impossible. Guidance, coordination, and external support vanish into irrelevance. A single overlooked problem may remain undetected until it becomes critical. In isolation, the crew or automated systems must solve every issue independently, using resources that are finite and knowledge that may be incomplete. The consequences of miscalculation are magnified by distance and time. Even the vacuum of space is not empty. Interstellar dust grains, tiny and fast, can erode spacecraft over time. Collisions at high velocity release immense energy locally, capable of puncturing hulls or damaging sensitive systems. Shielding against such impacts requires mass. More mass increases propulsion challenges, creating feedback loops of engineering difficulty. There is no environment that is truly benign. Every physical principle imposes a constraint. Every particle is a hazard. Every photon is a challenge. The problem is multiplicative. Radiation, micrometeoroids, thermal cycles, human factors, biological degradation, redundancy complexity, navigation drift, life support failure, propulsion limitations. Each interacts with the others. Failure modes do not exist in isolation. They cascade, amplify, and compound. Even the most advanced hypothetical designs, using materials and technologies centuries beyond our current capabilities, would face a web of interlocking risks that grows denser the longer the mission continues. And there is one more consideration: cosmic unpredictability. Supernovae, gamma-ray bursts, rogue asteroids, magnetic anomalies, interstellar clouds. Events that are extremely rare locally become almost inevitable over the timescales required for interstellar travel. A civilization can survive these on a planetary scale through redundancy and adaptation. In interstellar space, where resources are finite and isolation is absolute, even a single such event can doom a mission. Probability favors the universe. The longer you exist in it, the more likely something will break that you cannot fix. This is why engineering is both heroic and ultimately fragile. It can produce wonders, spacecraft capable of surviving months or even years, supporting life in orbit, crossing the solar system, or even reaching neighboring stars at sublight speeds with extraordinary effort. But the universe scales differently. Time amplifies risk. Distance compounds uncertainty. Complexity multiplies failure. No matter how clever, no matter how redundant, no matter how patient, the physical reality of the cosmos ensures that interstellar engineering is an exercise in perpetual hazard. The lessons here are stark. The best ships fail, not because we lack ambition, not because we lack intelligence, and not because physics is cruel. They fail because reality enforces interaction among countless constraints simultaneously. Energy, materials, biology, entropy, radiation, navigation, and time do not forgive imperfection. Redundancy cannot eliminate inevitability. Even minimal errors accumulate over decades or centuries into catastrophic consequences. Engineering is heroic precisely because it is finite. Every mission that dares to stretch across the stars becomes a study in trade-offs, mass versus energy, redundancy versus complexity, life support versus durability, speed versus stability. Every design choice has long-term consequences. Every assumption becomes an implicit bet against decay, degradation, and randomness. The universe does not allow perfection. It allows only temporary mastery. This is why interstellar travel remains an extraordinary challenge, not merely in propulsion or theory, but in practical, sustained survival across time and space. Even the most advanced ships, designed with perfect foresight and limitless resources, remain fragile monuments to ambition. They succeed not by defying physics, but by surviving against its relentless, patient laws. And yet, humanity continues to imagine, design, and plan. Perhaps this is the most human aspect of all, the refusal to accept ultimate fragility as final. Even knowing the odds, we calculate, we model, we simulate, we dream. Engineering becomes a form of hope, a bridge between imagination and possibility, even when possibility itself is constrained by cosmic reality. But hope does not remove the universe's constraints. It only frames the struggle. Even the best ships, armed with perfect knowledge, superior materials, and infinite patience, operate under a constant shadow. Failure is not a question of if, but when. And when we confront that inevitability, a profound truth emerges. Interstellar travel is not merely a technological problem. It is a lesson in humility. It is a recognition that ambition, intelligence, and creativity encounter boundaries, not as punishment, but as consequence. Engineering is not magic. It is negotiation with reality, and reality is patient. The universe does not hurry. It does not bend. It waits. Even after confronting the unyielding speed limit, the passage of time, the cosmic limits of intelligence, and the engineering challenges that threaten every mission, one barrier remains both intimate and inescapable: humanity itself. The greatest danger to interstellar travel may not be physics, propulsion, or energy. It may be the fragile architecture of the human mind, the social networks we depend upon, and the civilization we carry with us when we leave Earth behind. Long-duration space missions expose humans to extremes that no organism on Earth has ever endured. Days, weeks, and months in microgravity already reveal the profound stresses of isolation, confinement, and sensory deprivation. Astronauts report subtle but measurable cognitive decline, disrupted circadian rhythms, irritability, and anxiety. Sleep patterns fragment, hormones shift, immune systems fluctuate unpredictably. These effects are manageable in months-long missions because Earth is always just hours away. Even psychological support, emergency evacuation, and resupply are possible. Interstellar travel operates on a scale entirely different. There is no return to home. There is no resupply, no immediate backup. Months stretch into years, years into decades, and decades into centuries. Even with perfect engineering, perfect cryogenics, or perfect life support, humans remain biological creatures with evolved limits. Cognitive and emotional systems are not optimized for isolation across generational spans. Sensory input, social feedback, and cultural grounding, essential components of mental stability, decay under conditions that no human has experienced outside imagination. Consider the problem of isolation first. The human brain is social by design. Neural pathways, cognitive development, and emotional regulation depend on interaction, feedback, and community. Extended absence from social complexity, coupled with a limited environment, produces measurable maladaptation. Tasks that require judgment, creativity, or collaboration deteriorate. Confined groups are prone to conflict as stress amplifies minor irritations. Small disagreements escalate, and without external mediation, they can destabilize an entire social system. Now imagine this dynamic magnified across decades. A generation ship traveling to a nearby star may have a crew of hundreds or thousands living in an enclosed ecosystem. Every interpersonal friction, every subtle miscommunication, every unresolved conflict accumulates over time. Generational turnover introduces new cultural dynamics. Children grow up knowing only the ship as their world. They inherit the social frameworks imposed by their parents, but with subtle mutations. Language evolves. Norms shift. Values drift. Over multiple generations, the mission's original purpose becomes legend, then myth, then irrelevant story. Motivation decays not because of laziness or neglect, but because human psychology is bounded by comprehension, identity, and experience. The crew may survive physically, but the civilization on board can diverge unpredictably from the mission's goals. Isolation is compounded by monotony. The interstellar environment is overwhelmingly uniform. Stars appear as fixed points. Space itself is dark and empty. Even with simulated environments, artificial ecosystems, or virtual realities, monotony becomes a stressor. The human mind craves novelty, unpredictability, and variation. Lack of these inputs leads to cognitive fatigue, emotional instability, and even hallucination in extreme cases. Over decades, these effects are magnified. Decisions once simple become clouded. Judgment falters, cohesion fractures. Communication with Earth cannot fully alleviate these problems. The speed of light imposes unavoidable delays. Even the nearest star systems produce years-long gaps in feedback. Real-time conversation becomes impossible. Advice, news, or instruction arrives decades late, often when circumstances have changed beyond recognition. The psychological comfort of connection is replaced by the slow drip of delayed historical communication. To the crew, Earth may feel mythological, abstract, or irrelevant. The more distant the mission, the more the homeworld becomes a concept rather than a reality. The problem is recursive. Isolation and monotony impact cognition, which in turn affects cooperation, engineering maintenance, and problem solving. A minor mechanical issue can escalate into a critical failure if human operators are cognitively impaired or emotionally stressed. Social discord reduces efficiency, increases mistakes, and erodes trust. In interstellar travel, trust is everything. Trust in systems, trust in each other, trust in mission continuity. When trust breaks, even a ship with perfect engineering becomes a death trap. Human psychology is not the only limit. Biology imposes constraints that interact with social dynamics. Fertility, aging, and population management become critical on multi-generational voyages. Genetic diversity must be maintained to prevent inbreeding. Medical care must anticipate decades of disease progression, unexpected injuries, and cumulative radiation damage. Even minor lapses in health management can propagate catastrophic consequences over multiple generations. A single undetected mutation, a single outbreak of illness, or a single failure in reproductive planning can have exponential effects on the onboard population. The interdependence of psychological and biological factors is profound. A population suffering mental strain is less effective at managing health, education, and resource allocation. a population with medical fragility is more vulnerable to stress and conflict. This feedback loop ensures that human factors are never merely operational concerns. They are existential constraints. Beyond the microcosm of the ship itself lies a larger societal issue. Civilization, culture, and knowledge are cumulative processes. Interstellar missions require the preservation of skills, education, and purpose across generations. Every generation must maintain, repair, and innovate systems designed by ancestors who may no longer exist in any meaningful sense. Knowledge degrades, instructions become unclear, skills are lost. Even advanced automation cannot compensate for the tacit knowledge encoded in human experience. The more complex the technology, the greater the risk that human factors will undermine it. Psychology also interacts with moral and ethical challenges. Decisions about resource allocation, life support priorities, and social hierarchy must be made in isolation, often under conditions of extreme stress. Even small ethical disputes can destabilize authority, trust, and compliance. The social contract on board a ship is fragile, and maintaining order is not merely a logistical challenge. It is a continuous exercise in psychological governance. Cognitive limitations compound the problem of scale. Humans evolved to navigate Earth-sized environments with Earth-scale feedback loops. They are not optimized for managing decades-long projects with delayed consequences. Planning, decision-making, and foresight degrade with temporal and spatial scale. Even with rigorous training, simulation, and guidance, humans are prone to misjudgment in conditions that extend far beyond evolutionary experience. The further a mission stretches into time, the more fragile the human decision-making process becomes. Psychology also imposes limits on innovation. Crisis often sparks creativity, but prolonged stress can suppress it. Repetitive environments, scarcity of stimuli, and social tension reduce divergent thinking. The longer a mission continues without novelty, the more likely cognitive decline will undermine the capacity to solve unprecedented problems. Exactly the scenarios that interstellar travel is likely to present. Then, there is leadership. Human factors cannot be reduced to individuals alone. Group dynamics, hierarchies, and decision-making processes are critical. On Earth, hierarchies are reinforced by culture, tradition, and external feedback. In deep space, these structures become isolated, brittle, and self-reinforcing. Leaders may lose legitimacy, factions may form, and cooperation may degrade. Social cohesion, the glue of civilization, becomes a rare and precious resource. Finally, consider purpose. Human motivation is tethered to meaning. Interstellar travel requires sustained commitment to a goal that may span generations. Original crew members cannot complete the mission themselves. They must inspire descendants to continue work whose significance may be increasingly abstract. Without compelling purpose, discipline and cooperation erode. Historical examples of long-term projects on Earth, from megastructures to colonies, show that maintaining collective motivation across generations is exceptionally difficult. In space, this challenge is magnified by isolation, risk, and sensory deprivation. In sum, human factors impose an invisible but unyielding barrier to interstellar travel. Engineering may provide life support, propulsion may reach a fraction of light speed, materials may resist radiation. Yet the fragile interplay of psychology, social dynamics, cognition, and civilization introduces failure modes that no technology can fully mitigate. The most advanced spacecraft, the most resilient engineering, the most ingenious propulsion, all face ultimate limitation at the interface between mind and environment. Humanity is not an abstraction. We are fallible, emotional, social creatures bound by biological and cognitive laws. Space does not forgive these limitations. Isolation, monotony, generational drift, cognitive fatigue, ethical dilemmas, and social friction accumulate silently, relentlessly, and invisibly. Interstellar travel is therefore as much a challenge of civilization and psychology as it is a challenge of physics and engineering. Any plan that neglects human factors is doomed to fail, even if all other constraints are solved. The universe may tolerate matter, energy, and information, but it does not bend to the fragility of the human mind. Perhaps the ultimate frontier is not the stars themselves. Perhaps it is the challenge of sustaining humanity, not as isolated individuals, but as coherent, motivated, resilient civilizations across time, space, and uncertainty. The mind is both the vessel and the barrier. Conquer it, and interstellar travel may become conceivable. Fail to understand it, and even the most perfect ship becomes a coffin drifting silently among the stars. Every discussion of interstellar travel eventually confronts the stark arithmetic of reality. Speed, engineering, time, and human psychology define the physical and biological barriers. But there is another, equally inescapable frontier: economics. Not abstract accounting, not theoretical budgets, but the practical, relentless requirement for resources. Energy, materials, maintenance, and sustainability are the currency of survival in space, and on interstellar scales, they quickly become paradoxical. The economics of the impossible is not a hypothetical exercise. It is a fundamental law written into the universe itself. The first lesson is simple but devastating. Interstellar travel is extraordinarily expensive. Even optimistic projections of propulsion technologies demand resources that far exceed the total industrial output of Earth. A ship capable of reaching even a fraction of light speed requires fuel, energy, shielding, and structural materials measured in quantities beyond any historical precedent. To imagine such a vessel is to confront the limitations of extraction, production, and allocation. Every kilogram of mass accelerated to a significant fraction of light speed carries with it a compounding requirement for energy. The more ambitious the mission, the steeper the exponential cost curve. This is where the paradox emerges. To accelerate a starship to velocities that make interstellar travel feasible within human lifetimes, engineers must reduce mass. Every reduction of mass allows for less energy expenditure, but also decreases redundancy, shielding, and life support. Every safety feature, every supply cache, every system that prolongs survival adds mass, which increases energy requirements. The result is a feedback loop of escalating difficulty. Economically, this is a problem that no Earth-based industrial system is currently capable of solving. The cost of materials, manufacturing, and energy alone is staggering, without even considering ongoing maintenance and replenishment over decades or centuries. The second lesson is that interstellar travel is not a one-time expense. Resources must be sustained for durations that exceed political, economic, and social cycles. A mission launched today may require support decades into the future, possibly centuries. Funding must be maintained, not as a one-off expenditure, but as an ongoing allocation of capital, labor, and knowledge. History shows that even modest projects rarely survive such extended horizons. Great cathedrals, empires, and civilizations have collapsed before the final stones were laid. Interstellar missions magnify this risk thousands of times. Sustainability becomes not just an engineering problem, but an economic and societal one. Energy is the most fundamental currency of interstellar economics. Propulsion, life support, shielding, and computation all consume energy relentlessly. Solar power is abundant near stars, but interstellar distances remove this advantage entirely. Stored energy, nuclear reactors, or hypothetical fusion and antimatter systems must provide for decades, centuries, or millennia. Energy production and storage impose mass, which in turn increases energy demand, a recursive challenge that defines the starship cost paradox. No technology can fully escape it. The more ambitious the mission, the greater the compounding demands. Energy is both enabler and constraint. material resources present another paradox. Interstellar ships must be made of materials that are both extremely strong and extremely light. They must resist radiation, impacts, and the slow degradation of space itself. Composites, alloys, and advanced ceramics are candidates, but all require industrial capacity, rare elements, and precise manufacturing at scales unmatched on Earth. To produce enough materials for a single interstellar mission may consume a significant fraction of the planet's accessible resources. Multiply this by multiple missions or by generational replenishment, and the economic scale becomes mind-boggling. Humanity may theoretically possess the knowledge to construct such ships, but not the practical ability to source and allocate the resources without collapsing other vital systems. Logistics further amplify the paradox. Every component must be produced, tested, launched, and integrated. Every system must be redundant and repairable. Every supply chain, no matter how long, must remain intact over decades. On Earth, global supply chains are fragile. Just-in-time manufacturing and economic dependencies create vulnerabilities. In space, these vulnerabilities become existential threats. An overlooked flaw in a microchip, a delayed delivery of raw materials, or a miscalculated margin in energy stores could render an entire mission catastrophic. The economic scale required to mitigate these risks is staggering and grows non-linearly with mission duration and distance. Sustainability introduces yet another layer. Interstellar missions cannot rely on resupply from Earth once underway. Life support, fuel, and repair materials must be recycled and regenerated indefinitely. Closed-loop ecosystems, hydroponics, bioreactors, and chemical recycling are essential. Each introduces new engineering complexity, and each is itself a resource sink. A single system failure can cascade into failure of multiple other subsystems, threatening crew survival. Economically, this is a continuous cost. Energy, mass, and time are all consumed merely to maintain the viability of the mission. The longer the mission, the higher the compounding cost, both in resources and risk. This brings us to the social-economic paradox. Interstellar travel requires collective commitment across generations. Funding a multi-generational mission is not merely a technical or financial decision. It is a cultural one. Societies must prioritize missions whose payoff may occur centuries later, long beyond the lifespan of decision-makers, political systems, or economic cycles. History offers countless examples of ambitious projects that failed because societies lost interest, funding, or focus over time. Interstellar travel amplifies this problem. The project spans centuries. Isolation compounds uncertainty, and human psychology prefers short-term reward. Funding alone cannot guarantee survival of the mission. Sustained economic and cultural alignment is required, a level of stability humanity has rarely achieved even on Earth. Risk assessment is further complicated by uncertainty. Interstellar missions encounter hazards that are rare, extreme, and unpredictable. Micrometeoroid impacts, supernova radiation, propulsion anomalies, and unexpected biological challenges all impose stochastic economic costs. The expected value of resources required to mitigate these low-probability, high-impact events grows exponentially with mission duration. Economic planning becomes a calculation of improbability. The paradox is that the more one invests in safety, redundancy, and contingency, the greater the resource requirement becomes, often exponentially. At some point, the costs exceed practical limits. And yet, the allure of interstellar travel persists. It promises new worlds, survival beyond Earth, and expansion of knowledge. But every promise must be balanced against the economics of impossibility. Resources are finite, energy is expensive, time multiplies risk. Every kilogram of material, every watt of power, every hour of human labor carries an invisible cost that compounds across space and generations. To fund such missions without collapsing existing civilization is not merely challenging, it may be impossible within our current planetary economy. This is where the starship cost paradox becomes clear. The more ambitious the mission, the greater the resource requirement, the longer the duration, and the higher the risk of failure. Yet the mission's goal, interstellar presence, depends on exactly those same factors. Energy, mass, and time are simultaneously the enablers and the constraints. You cannot have one without exacerbating the others. Any solution that seems feasible on paper, when scaled to the reality of decades-long, self-sustaining interstellar missions, confronts a horizon where economics, physics, and biology intersect to impose unavoidable limits. Some theorists propose solutions, self-replicating machines, automated construction of habitats en route, or mining of interstellar medium for fuel. These ideas are intellectually fascinating, but they introduce new layers of complexity. Replicators require materials, energy, and control systems that are themselves enormous engineering feats. Automation cannot fully replace human ingenuity, especially when unexpected circumstances arise. Even minimal failures in self-replicating systems propagate exponentially over time, creating cascading economic and survival costs. Moreover, interstellar economics is not isolated from planetary economics. Humanity cannot divert the entire industrial output of Earth to a starship without jeopardizing the stability of civilization itself. Resources devoted to interstellar travel reduce resources available for food, medicine, energy infrastructure, and planetary resilience. There is an inherent trade-off between survival at home and ambition among the stars. The economics of interstellar travel is therefore inseparable from the economics of human civilization. Risk, cost, and sustainability are intertwined across scales. The paradox is further compounded when considering human factors. Multi-generational missions require not only physical resources, but cultural and psychological resources. Training, education, social cohesion, and motivation are all consumable assets. They cannot be preserved passively. They must be actively managed, reinforced, and renewed. This introduces invisible but critical economic costs. The value of human attention, cultural continuity, and psychological stability becomes as important as mass, energy, or fuel. Neglect any of these, and the mission fails, regardless of technical success. Ultimately, the economics of the impossible is a lesson in humility. It shows us that ambition cannot be divorced from reality. It demonstrates that even if we possess the knowledge, intelligence, and engineering capability to design interstellar vessels, resource limits, energy constraints, sustainability challenges, and generational continuity impose ceilings that are rarely discussed. The paradox is that the very factors enabling travel also multiply its difficulty and cost. The universe permits ideas, dreams, and plans, but it does not forgive oversight, optimism bias, or failure to account for compounding costs. And yet, humanity persists. We calculate, simulate, fund, and dream. We measure costs in terawatts, tons, and decades, and we still imagine voyages to distant stars. The starship cost paradox is not an argument against interstellar travel. It is a mirror reflecting the limits imposed by reality, time, and ambition. It forces us to confront the gap between imagination and practicality, between desire and feasibility. The paradox teaches us that interstellar travel is not simply a technological challenge, a matter of building faster engines or lighter ships. It is an economic challenge, a societal challenge, a moral challenge. To send humans across the stars is to commit civilization to an unprecedented, sustained allocation of resources, energy, and attention, an undertaking whose failure is always possible and whose cost is never truly finite. In the end, the economics of interstellar travel may be the ultimate arbiter. Physics and biology define what is possible. Engineering defines what is survivable. Psychology defines what is sustainable. And economics defines what is achievable. No interstellar mission can succeed without addressing all four. The paradox is unavoidable, the challenge immense, and the stakes existential. The stars beckon, but the ledger waits. The universe demands payment in resources, time, and energy, and it collects relentlessly, whether we succeed or fail. After decades of imagining the stars, of dreaming about distant worlds, of calculating trajectories across light years, one truth emerges with unyielding clarity. Interstellar travel may not be a matter of if, but of limits. The dream is vast, breathtaking, and inspiring. But the universe is patient, impartial, and unforgiving. We began by confronting the immutable speed limit. Nothing travels faster than light. Even the most optimistic scenarios, fusion drives, antimatter engines, photon sails, yield fractions of light speed, stretching missions across decades or centuries. Time dilation offers only modest relief, allowing travelers to experience subjective time at a different rate than those left behind. But the universe itself stretches around them. Distances are enormous, isolation is absolute, and the stars recede as quickly as our ambitions can approach. No matter how clever the design, the cosmic speed limit is absolute. Then came the engineering reality. Even if speed were no obstacle, constructing a vessel capable of surviving interstellar space is a monumental task. Materials must resist radiation, micrometeoroid impacts, and thermal extremes. Propulsion systems must function for decades without maintenance. Life support must operate without resupply. Redundancy multiplies complexity, and complexity multiplies failure. Even with hypothetical future materials and technologies, the feedback loops of mass, energy, and durability create a landscape where perfection is impossible and failure is inevitable over time. Human factors introduce yet another dimension of challenge. The mind, fragile and evolved for Earth, confronts isolation, monotony, and generational drift. Social structures strain under confinement. Cognitive fatigue, stress, and conflict accumulate. Motivation and purpose may degrade across generations, fracturing mission cohesion. Civilization itself, the repository of knowledge, culture, and expertise, must survive alongside the crew. Yet isolation and entropy relentlessly erode it. Survival is not only about engineering, but about the human spirit. And the human spirit is bounded by psychology, biology, and society. Then comes economics. Interstellar travel is not only expensive, it is almost unimaginably so. Energy, mass, and resources scale exponentially with ambition. Multi-generational missions require sustained funding, societal commitment, and careful allocation of resources over decades or centuries. Energy must be generated, stored, and conserved. Materials must be produced, tested, and maintained. Knowledge must be preserved. Every additional layer of safety, redundancy, or sustainability adds mass, which in turn increases energy demand. The starship cost paradox is unavoidable. The more we invest in enabling interstellar travel, the greater the resource and economic burden, until practicality fades into impossibility. Even if all these barriers could be mitigated, there remains a final truth: uncertainty. Cosmic hazards are unpredictable. Micrometeoroids, gamma-ray bursts, interstellar dust, and unknown phenomena could end missions in an instant. Engineering, psychology, and economics can only reduce risk. They cannot eliminate it. Over decades and centuries, even a minor oversight becomes magnified, cascading into failure. The universe does not forgive error, nor does it bend to desire. And yet, interstellar travel continues to inspire. Why? Because it is human to imagine, to plan, to hope beyond limitations. Even in the face of absolute constraints, we calculate trajectories, design starships, simulate ecosystems, and speculate about the unknown. We dream because the act of dreaming transforms understanding, fuels innovation, and expands the boundaries of knowledge, even if the ultimate goal remains unattainable. Perhaps the greatest lesson of interstellar travel is humility. It teaches that ambition encounters limits in multiple dimensions: physics, engineering, biology, psychology, and economics. Each is a wall that cannot be moved. Each imposes constraints on the scope of possibility. To understand interstellar travel is to understand that the universe is not an obstacle to overcome, but a framework of laws to respect. The stars are not ours to reach easily. They are reminders of scale, patience, and consequence. Yet there is also a subtle, paradoxical optimism. Interstellar travel may always be a dream in practical terms, but it is a dream that drives exploration, innovation, and reflection. Every calculation pushes physics forward. Every simulation expands understanding of biology, materials, and engineering. Every discussion about multi-generational missions illuminates the fragility and resilience of human society. Even if the stars are unreachable, the journey toward them teaches lessons about ourselves, our civilization, and our place in the cosmos. Interstellar travel may be impossible in practice, but its pursuit is profoundly human. The ambition to reach the stars reflects our curiosity, our courage, and our imagination. It confronts us with our limits, physical, mental, and economic, and forces us to grapple with the scale of the universe. It reveals the intricate interplay of speed, energy, materials, psychology, and resources. In confronting the impossible, we learn to appreciate the delicate balance that sustains life and civilization on Earth. History provides a parallel. Humanity has always reached for what seems beyond reach. Great voyages of exploration, monumental constructions, and scientific revolutions were once considered impossible. Even when the oceans threatened to swallow ships or mountains seemed insurmountable, ambition and ingenuity prevailed, but always within the bounds of reality. Interstellar travel is the ultimate iteration of this pattern. It stretches human ambition to the limits of understanding, but reality imposes a ceiling that no courage, intelligence, or wealth can surpass completely. So why does interstellar travel remain a dream? Because the universe is vast beyond comprehension. Time is relentless, energy is finite, and humanity is bounded by biology, psychology, and society. It is not a failure of imagination. It is a consequence of scale. To bridge the distance between stars is to confront the full spectrum of constraints: the speed of light, the fragility of matter, the endurance of human minds, the sustainability of civilization, and the cost of resources. Every dream encounters these barriers eventually, and interstellar travel collates them all into one ultimate test. And perhaps that is the most important truth. Interstellar travel is as much a mirror as a goal. It reflects our ingenuity, our audacity, and our limitations. It forces us to quantify ambition, to measure risk, and to recognize the delicate balances that sustain life and society. Even if we never reach another star, the pursuit shapes our understanding of physics, engineering, psychology, and economics in ways that are deeply consequential on Earth. The stars themselves do not beckon because they are close. They beckon because they define the limits of possibility. They challenge us to confront time, distance, and consequence. They remind us that scale matters, that preparation matters, that human endeavor, while extraordinary, is bounded by laws we cannot change. In the end, interstellar travel may always remain a dream, but it is a dream worth having. It compels us to think across centuries, to manage civilizations, to innovate, and to understand ourselves in unprecedented ways. The dream may be impossible, but the act of striving transforms the possible on Earth. The lessons, from physics to psychology, engineering to economics, enrich humanity, even if the stars themselves remain out of reach. Perhaps the final lesson of interstellar travel is humility paired with aspiration. The universe will not yield easily. It imposes limits on speed, survival, and resources. But by confronting those limits, humanity gains perspective, knowledge, and understanding. The impossible shapes the possible. The unattainable shapes civilization. And the dream itself, even unrealized, illuminates the fragile, magnificent, and audacious nature of being human. Interstellar travel is more than a journey. It is a reflection. It is a test of ambition against reality. And in the quiet, patient expanse of the cosmos, even the attempt teaches lessons that no starship could carry. Lessons about endurance, wisdom, restraint, and hope. The stars remain distant, our ships remain grounded, but the human mind continues to reach, to imagine, and to learn. And in that, perhaps lies the true victory. Not in reaching the stars, but in understanding the universe and ourselves well enough to measure the impossible and to strive anyway. History will judge the dream not by whether it succeeds, but by what it teaches along the way. And in the end, that may be the most human journey of all.